Next up, we have Christopher Krupiarz, a member of the principal professional staff here at APL. Mr. Krupiarz is a member of the principal professional staff and the autonomy lead for the Interstellar Mapping and Acceleration Probe mission. Mr. Krupiarz has over 20 years of experience in spacecraft software development and management. He developed flight software for the Messenger, Van Allen probes, New Horizons and New Horizons missions, and also the Parker Solar Probe mission, where he was the flight software lead. In addition, Mr. Krupiarz was the JHU APL principal investigator for exploring the use of delay-tolerant networking for space communication, and served in several line management roles within the APL Embedded Applications Group. Chris is also the founder of the Flight Software Workshop and served as chair starting in 2007. So we're very excited to welcome him back to the workshop as our first welcome speaker this year, presenting flight software at JHU APL. Chris, it's all yours.
Okay, can you see me okay?
We can see you just fine.
Excellent. Well, I'm glad you can see me fine. This is a rare event for me to actually be on camera 2 years into this whole pandemic thing, and I still just don't like being on camera, but that's here's your special treat to see me in person. A lot of the folks even at APL haven't seen me in I guess a number of years now. But anyway, as Brandon said, my name is Chris Krupiarz, and I, as Brandon said, was originally working on the Flight Software Workshop back in 2007. I'll talk a little bit more about that later. Again, a little bit of my background, flight software from 2000 at APL up till now, and also now the autonomy lead on IMAP. One of the advantages of having these workshops normally when we're in person is an opportunity to see a little bit more about our various locations. This has been at APL. I think it's been at Marshall at one point. It was at JPL. An opportunity to sort of see what it is that we do. Unfortunately, we can't do that in person, so I can't give you a tour or anything like that. But I'm going to try to give you a little bit of overview of what APL does and what we do for flight software here at APL. So APL is the Applied Physics Laboratory. It's part of the Johns Hopkins University. It's not in Baltimore. I don't know how many times I'm asked, oh, you work in Baltimore, when I say I work for Hopkins. And I'm not at the hospital either, which is another question I'm frequently asked. But we are the Applied Physics Laboratory. And as part of Hopkins, we are a UARC, a University Affiliated Research Center. And what it is that we do, if you walk the halls of APL, you'll see pretty much every array possible of STEM type work going on here. So I'm a computer scientist. We have chemical engineers and mechanical engineers and all sorts of arrays of mathematicians and planetary geologists, everything you could possibly imagine that a lab would have. And of course, we have an extensive support personnel that keep everything operating efficiently and effectively in order to get our work done. Our sponsors are an array of government organizations. NASA, of course, is one of our sponsors when we're talking about here about space. But we also do a lot of work for the Department of Defense, Homeland Security, the intelligence community, and also other organizations within the government. And what is our purpose? It's one of our former directors had a slogan called critical contributions to critical challenges. And that really is the essence of what we do. When the government has a difficult problem it's faced and they either want to implement it or ensure that it will operate properly, they'll come to APL in order to get that work done and make sure that everything is working the way that it should. And we have over 7,200 staff members. I think we're approaching, and I should have looked this up directly, but I believe we're right around 1,000 within the Space Department at this point, or the space sector. And it's grown significantly even since when I started in 2000 in terms of not only the work we're doing, but also the personnel that we have here. We have an array of abilities that we have across various sectors within the lab. And our primary work actually began in World War II, and that's when the lab was founded. And we were asked to develop a proximity fuse. And a proximity fuse, of course, is something that explodes a little bit closer to the target than actually hitting the target. And it was able to determine that autonomously. And the work that we did for that in particular during World War II helped to fight against the kamikaze pilots. It also worked in terms of preventing the V-2 rockets from hitting England. And it was also used in the Battle of the Bulge in terms of attacking infantry during that conflict. And that sort of work that we've done within the DoD has extended throughout the Navy and other areas of DoD. If you look at the work that we do, it's primarily in terms of the overall effort in terms of people. It's for the Navy, and we serve a role that's called the trusted agent, where the government will come to us and say, here's a system that's been developed or a system that's going to be developed. And our responsibility is to ensure that that system will either operate as expected or that it is operating as expected. And that's where a lot of the work actually goes on. And the other work that we do as well can be research work. You may have heard a couple of years ago, the work that we did with DARPA for their prosthetic limb. That was done by our research organization. And again, many other areas that we're functioning in. And today I'm going to focus, of course, on the space science and engineering, or our space exploration sector. And one of the things that I enjoy, one of the things that I think is an advantage at APL, and like I said, that I enjoy, is the fact that we are able to do end-to-end missions. So we have competencies that go across the entire array of what a space mission can do, starting with the research that we do. Now, normally, if I was in the office, I would say a couple of floors below me, you would see a whole bunch of scientists. Well, unfortunately, a couple of floors below me right now is the basement, and there are no scientists in my basement right now. But I would say that they run the gamut of space exploration. So you're talking about planetary geologists, you're talking about astronomers, heliophysics experts, and they do a lot of research and a lot of publications across the board, pushing the technology that we can work towards in order to expand our understanding of space. The advantage of that, of course, is that when we have scientists that are doing all of that research, they come up and say, hey, you know, it would be really cool if we could just do this one extra little bit of mission and define it a little bit more. And then I can understand a little bit more of that area that I'm examining at that point. So that's when we come to the phase of doing conceiving of various different missions. And that's not only in order to do things like discovery proposals or new frontiers missions or something along those lines. We are also sometimes asked by NASA to develop new concepts, for instance, for decadal studies. Now, I worked on a couple of those last year. One was a Pluto orbiter, and the other was a Mercury lander. So what happens there is we have an ACE lab, what we call an ACE lab, where we get a bunch of engineers and scientists and program managers and folks like that together to say, well, how can we push this limit? How can we achieve something that we haven't done before? I really enjoy these because you're looking at the technology that we're going to see in the future. I know a lot of the flight software people there are kind of used to having to sort of push it a little bit because, you know, you can't really make big changes mission to mission. But this sort of gives us an opportunity to say, here's something that we're going to do a decade from now. And it allows us to say, here's technology that we're examining in a research phase. This is how we'll be able to employ it into the future. That's one of the nice things about working on some of these advanced concepts. And hopefully, eventually, some of these advanced concepts are accepted as a proposal, and we come up to the design phase. And the design phase, for those that have worked on NASA missions, we're talking about phase A, pre-phase A, that concept where you're saying, you know, this technology ready? Is this something good? Can we do it? Are we going to be able to achieve the goals that we're setting out to do? And we can put that into motion. And then hopefully all that work that we did during the previous conceptual phases and the work that we'll be doing in research gives us an opportunity to employ some of that new technology into new missions. Once the design phase is complete, arguably, I still think it's the most enjoyable phase. I mean, some folks can enjoy the design part of it, but I really like when we start to build stuff. And that's when you start to see things really start to happen in terms of both the flight software and the actual hardware itself. Again, if you were here, hopefully we would have a mission available. But one of the things that I still find really exciting about working on these programs is being able to go down the road to our INT lab or our environmental facilities and see what was PowerPoint slides just a couple of months ago starting to become real. And that's one of the more enjoyable parts about seeing a mission evolve over time, is to see the pieces that are going together until you get to the point where we have a completed spacecraft and it's ready to go on and do the great things that it was meant to do. And during that, the building phase, of course, we have the test phase, and that's where I was just discussing, of course, the INT that we have, integration and test, where the spacecraft is built, tests are run, we go down and hope everything works, and of course, most of the time, well, I was going to say most of the time it doesn't, but most of the time it does. But there are those moments when it doesn't, and they're both exciting and stressful and everything else that makes these missions great. And we have test facilities here at APL, and we also take advantage of the larger test facilities down at the Goddard Space Flight Center where they have more extensive ability to do some of the more extensive tests that we need to do in order to ensure that missions are successful. And then finally, we get to launch and we get to the operations. We have our several operations facilities right now. Thinking through how many spacecraft we currently have operational, it's like 6 or 7, I believe. And each of those, of course, has their own operational facility here at APL, from which we send and receive, send commands, receive telemetry, get the data back, that critical data that we've been looking at, the critical data that sometimes we've been waiting decades to see. You look at something like Solar Probe, conceptually, that was like literally decades that we've been wanting to do a mission like that until we finally were able to get the technology. They were able to get it. And the first data that we got back from that encounter was just invaluable in terms of the research that will be able to be employed, which again feeds into that last piece. So we get to operate it, and then we get the data down, feed it back to the scientists. The scientists take a look at that data joyously and say, oh, we finally got to figure out that one piece of the puzzle that we were looking for, but then we now have this other piece of the puzzle we'd like to figure out. And at that point, we do the cycle all over again. So a good example of that is that we had New Horizons. We had an ACE study where we had a Pluto orbiter. Maybe someday we'll do a Pluto orbiter and learn a little bit more about that I'm going to say planet, that planet. So here's a listing or a visual graphic representation of all the missions, or a lot of the missions that we've done over the course of many years. Brandon mentioned I worked on Messenger. I worked on Messenger New Horizons, and also now working on IMAP. We have Solar Probe that's up, doing its encounters with the sun. I did want to call attention to NEAR because that's one of the sort of the crux or the turning point, I believe, at least in my mind, of what APL did. You may recall Dan Golden back in the 1990s had the better, faster, cheaper plans. One of the offshoots of that was the Discovery program, and NEAR sort of retroactively became one of the first missions that was part of the Discovery program. And that mission was the ability to take a look at an asteroid, and eventually we even landed on it and were able to get data back on a very cheap and effective way of doing it. And that's sort of set the tone, I believe, within APL to do many of the other missions that we've been able to do of that type. I also remember when this was prior to my time of NEAR, but I was out in a different company and looking at the website for NEAR and seeing those pictures come in. I was just amazed that just a short ways down the road from where I was, that we were able to communicate to this spacecraft so distant and to get such new information. It was just fascinating to see the work that they were doing there, or the work that I then ended up joining. And we also do instruments. We have an array of those currently operating, an array of missions or instruments that are going to be operating. And we've had our former head of the Space Department who has a claim to fame that he has actually worked on instruments that have gone to each of the planets in the solar system. And again, including Pluto as a planet for the purposes of this discussion. But we don't only do civil space, we also do national security space. And our national security space started back at the beginning of the space age, just a short time after the original Explorer was launched. This is a story that's often told about APL. There were a couple of physicists that were working at APL. They observed the Doppler effect of the Sputnik satellite that had been launched by the Soviets, and realized that you could take, if you know where the satellite is, you can know where you are in space. And they took that technology as a precursor to the GPS work and created the transit satellites. If we were here at APL, you'd see one of our transit satellites in the lobby. And that, again, was a forerunner for what we now heavily use in terms of GPS in order to understand where we all are on the Earth itself. Another satellite that I wanted to mention here was the GeoSat satellite, which was able to do work in terms of understanding levels of the oceans, again, work that we would have done for the Navy. Some more missions that we had for NSS. MSX was one of our largest one. I believe it was the largest spacecraft that we had ever worked on. It was a Star Wars spacecraft that was looking for ballistic missile launches, looking for infrared on that. I also learned actually just recently that the rocket, the Delta II rocket that launched MSX, which is, it was the first time, I don't know if this is correct anymore, but it was the first time knowingly that somebody actually got supposedly tapped on the shoulder by a piece of the rocket as it had re-entered the atmosphere, after it had re-entered the atmosphere somewhere, and I think it was in Tulsa. I had never known that until last weekend, which I thought was really interesting. Almost thought it wasn't true, but then I looked it up and it appears to actually be true. And then we also have a couple of CubeSats that we started in 2013 as we went on that road for a little while within the NSS world. We developed in-house, we developed a CubeSat called the ORS spacecraft that were called Jake and Elwood at the time, after the Blues Brothers. And that was done to work on tactically responsive space. So the ability for people in the field to identify what's going on tactically as quickly as possible. And that was followed up by another CubeSat that we worked on called CAT that was responsible for another test that we had. And this one we actually had the bus developed out of house, and we added in the systems engineering aspect for it. And now I'm going to go through some of the highlights we had at APL. This, of course, is Dragonfly. It's long into the future, but we're working on this now in terms of getting some of the testing done and demonstrating the capability to do a quadcopter. Obviously one of the more exciting missions that we've done, and one of the more creative ones that went through our process. And just to give you a little bit more background about our software heritage, this slide shows at the start of feeding in 3 different missions, but really we go all the way back to a spacecraft called ACE that we developed in the 1990s. And Steve Williams, who is one of our former employees, I wish he was online here, because his work that he did, he still has code running on our systems that he developed in the 1990s, which to me is amazing that we have the ability to have that heritage and such a solid array of code that's operated across so many different missions. But the 3 that I mentioned here are kind of the main feeders into what the code that we have now. We have New Horizons, Messenger, and Stereo. Messenger and Stereo were pretty much developed at the same time, and New Horizons slipped in a little bit after that. And we came to a realization that trying to maintain multiple lines of code like this, multiple sources of code like this, can be difficult. We had a concept that we called Modify Last Mission originally, which is where we would take things like, okay, we're going to do this next mission, let's just take Messenger and make a duplicate of it and go on. But unfortunately, if you had other missions going on, you didn't really get the benefits of some of the technology that were introduced like that. And that's what I'm going to have a follow-on to that in some of these slides that are coming up. We came to that realization that having that common source not only allowed us to reduce cost, but it also allowed us to introduce that new technology. So we introduced an IRAD right around 2000, it was like 2008 or 2007 or 2008, which strove to do exactly that. Now we looked at the possibilities that we could work on in terms of putting that forward. Should we look at something in-house for a common software capability? Should we look at a CCSDS standard at the time that we examined? Well, we came to the realization that we have this really great partnership with folks down the road at the Goddard Space Flight Center that had developed the core flight executive. And we looked at that and said, wow, this is really nice code. It's well documented. It's operated on multiple spacecraft. This would allow for a great foundation going forward to add in this heritage code. And that's exactly what we did. We incorporated the core flight executive into our system, and then took all of the applications that were critical to us that had developed on New Horizons, Messenger, Stereo, and all the other systems, and put that on top of the core flight executive. And that allowed us a great leap forward that we never would have been able to do as quickly as we did without the help and the assistance and the opportunity to have worked with Goddard to get that incorporated into our flight software. So the first mission that did that was the Van Allen probes, also previously known as the radiation belt storm probes. And that was highly successful opportunity to incorporate that. Now, the next step, it's great if you do it once. If you have some reasonable code, and then, it's a lot of times they'll kind of all fall apart after that. But we were able to take that and then incorporate it into Parker Solar Probe, taking advantage again of a tremendous amount of reuse that reduced significantly the cost that we would have faced in terms of developing Parker Solar Probe, and applied those towards adding in any new technology that we needed for Solar Probe, which was significant because we had 3 processors on Solar Probe, we had spaceware, we had some new technology that we had to incorporate. And that allowed us to focus on that new technology as opposed to, once again, repeating this, modify last mission capability and work towards achieving the goals of that mission. That then became, I actually then branded it. So this is the step forward that we made now, is that we are taking the Parker Solar Probe code and it becomes part of the overall flight software system. And in the flight software system, we have the flight software core. And the flight software core is that core product that then is used for multiple missions. And so that was used on DART, is going to be used on IMAP and Dragonfly, and hopefully also be used on any future missions that we come across on into the future. And that, again, is the sort of the foundation and that allowed us to move forward as quickly as we could in that fashion. Now, I talked about on the previous slide about incorporating technology. And this is what I want to sort of give you a sense of as we walk through this next series of slides, is that each mission that we do is an opportunity to push that a little bit more, to find something that is needed for the mission, because you don't necessarily, well, you definitely don't want to incorporate technology that isn't required for the mission, but is needed for that mission and then can be brought back into the core flight software and have that available for future opportunities and future missions, whatever those may be. So this, of course, is a picture of Messenger. And one of the things that we were able to incorporate into Messenger was the CCSDS file delivery protocol. This is the first time that CFDP had been used in a deep space mission. It had been used orbitally by a, I think it was Surrey Technologies. It was a small, the company out of England that used that initially, but this is the first time that CFDP had been used in a deep space mission. And what CFDP really allows you to do, and something that the operations folks really appreciated, is that when you get the data down with CFDP, because of the checksum capability and all the other associated retransmission capabilities and everything associated with that, is that you know that it's good. They no longer had to look through all the data and say, oh, I want to get that piece of the SSR or that piece of the SSR and fix that part of it. It was all done transparently, which again is an opportunity to reduce mission operations and to allow for more successful transmission of that data. Another capability that we introduced into that was our RPN engine. So this is the ability to add in more complex mathematical expressions to our autonomy system. On board our spacecraft, we have an autonomy system that was developed, again, it dates back to the 1990s and some of our early missions, but it's also been very successful in its use. So it has a series of autonomy rules that examine a set of computed telemetry, which it just is variables that allow the information to be conveyed about how a specific subsystem is operating. It has an ability to have stored variables, which is just information. Think of them like parameters that you can tweak the way the system is operating. And then it has a series of macros, which are a set of commands that can operate. So every second, our autonomy system is operating and it observes the operation of the spacecraft. It's sort of, I mean, essentially is an expert system where it evaluates various rules and context and ensures that the system is operating properly. For a system like Solar Probe, where we have only seconds really to ensure that our spacecraft doesn't go off the sun or will have severe, very severe consequences, our autonomy system is critical to that operation, as it is for many other spacecraft as well. But this introduction of the RPN engine allowed us to have much more complex capabilities than we had had previously. Another example, this is the stereo. This is one of 2 stereos. So of course, stereo was a mission that was sent out in before or ahead and behind. So you think of one of the spacecraft as being ahead of us in the Earth in orbit and another one being behind us in orbit, and it was able to take stereo images of the sun. And the capability that was introduced there were our memory objects. And this allowed us again to have an uploadable, configurable capability for things like what I just mentioned, all the various macros and autonomy rules, storage variables, and things like that that were incorporated into our system. Memory objects incorporated in stereo, moved it into the to the CFE capability of RBSP, and now is available in our flight software course. So another example of where we had some technology that was different at the time, that when, even though we had messenger going on at the same time as stereo, we were able to take what the memory objects were and put it into this common code, even though we would have, instead of lost that capability if we simply did, say, modify last mission with the messenger code. This is New Horizons. One of the things that we introduced into New Horizons with the ability to have a beacon mode and hibernation. Hibernation, of course, is going to be used on Dragonfly. Beacon mode was something that's also been used on Solar Probe. Beacon mode is nice because when you don't have a lot of downlink capability, you can at least know the general state of your spacecraft. So we use that on Solar Probe when we are going around the sun and we don't have a full RF configuration, but we can at least get something back to say, hey, the spacecraft is fine, or hey, it's not, and y'all better be ready for this when you come back into contact. Which fortunately with Solar Probe, we've never had any of the latter. It's always been the former. We also had the ability to do automatic command construction. This is particularly important for the RTG because of the conditions that could change on board, and the round trip light time simply was not capable of modifying the commands that were needed to keep that under control if we had to have a person in the loop given the long round trip light times of New Horizons. This is an example. This is the CubeSats that I mentioned previously, the ORS-1, ORS-2 bus demonstrations. This is the first time that we had run a Leon 3FT, which then we also end up using in Solar Probe, and we've used in DART. I bring this one in particular because this was an example of where we had an NSS mission and we were able to incorporate that technology into the future into a SIB-space mission, and also the fact that it was a CubeSat. So we had a little bit more flexibility on what we were trying to do to incorporate technology quickly into a mission when we had a CubeSat versus some of the larger spacecraft that we had. And also the additional part of it that paved the way for use on Solar Probe was the use of the RTEMS operating system on these two spacecraft that we then ended up incorporating into our DART as well. And we'd be using that in IMAP as well. An example of how we can use an instrument in order to incorporate some of this is the mini RF spacecraft. This is the first, we had an instrument on that called, I'm sorry, the Lunar Reconnaissance Orbiter, and we had an instrument on that called mini RF. And that was the first time that we had done SpaceWire. And SpaceWire, much improved capability over something like 1553. It allows you to have a simple one location and where you can have the data coming in. And we use that on SpaceWire, on Solar Probe, and we're also using that on IMAP. I talked before about how we incorporated CFE. This is, again, the major point at which we made good progress in terms of moving forward on our standardization. And all thanks again to Goddard for having created all of this and allowed us to quickly incorporate it into our system. And our current mission of Solar Probe, we actually use CFTP on board to communicate between the two boards that we had, or the three boards that we have on there as well. And that's one of the highlights. It just shows you that while CFTP was designed for deep space transmission, the fact that we had developed this capability, had it on board, had it ready to go for our actual telemetry transmissions, it also allowed us to just use it on board as well to communicate between the two boards. And we also introduced conditional commanding into our autonomy rules, which is a big step forward, especially for something like Solar Probe, which is so complex that it was difficult to, it would have been impossible really without having the if-then structure in order to stay within the constraints of the autonomy rules we needed for Solar Probe. And finally, I just wanted to mention DART as an example of something that started with an IRAD many, many years ago internally to APL, and now is going to fly. And it's one of the most exciting step forwards that we made because we really have made a mission happen with this capability in a way that we hadn't done before with flight software. And that ability, of course, is going to be able to hit that moon and that asteroid just where we want it and help save the planet in the future, potentially. So that's my overview of the flight software at APL. And I just want to touch upon too that, like Brandon had mentioned, we had this idea. My roommate at the time, Annette Morantes, and I developed this idea that, you know, we do all this software, and at the time, it's been a lot different now, but at that time, there's a lot of difficulty in terms of getting communication across the various organizations. And we were thinking that that, yeah, we're all competitive. I will admit that I'm as competitive as anybody else when it comes to wanting to get the mission out there on a proposal when we go up against Goddard or go up against JPL or folks like Blue Origin going up against SpaceX or things like that. But at the end of the day, once the mission is awarded and that spacecraft is on the launch pad, we all want everybody to succeed, not only because it helps us, because if one mission succeeds, it's probably going to fund some other mission along the way, but just the fact that we're all trying to achieve, in many ways, pushing that human knowledge as far as we possibly can. And just that thought of going up against that common, I would just say common enemy of space, that we all want to succeed and we want to make sure that things happen. And our thought behind starting this workshop was that this is a chance to get us all together and talk about these kinds of things and be open about what goes right and what goes wrong. Here's the problems that we had. Here's the problems that we'd like you to avoid, because we want everybody to succeed. And that was the genesis of the workshop. And it started out in 2007. We had it again at APL in 2008. I've been reading a book about the Mercury program, and I kind of think of that as like our suborbital launches, because once we went over to JPL with Amalie helping it and really creating it over there, that's sort of the orbital step. Like initially it was a lot of folks that just locally, a lot of APL people, primarily Goddard people at the first workshop. But then once we went to JPL and it opened up to the broader community, that was a huge step forward that then has allowed us to maintain this and have so many, looking at the list of folks that are contributing this time around, it's just amazing. That's exactly what I wanted to have happen back then. It took a few years until we got to that level, but it's great to see that we have so much contribution from across so many different companies and labs and everybody else, and countries even. So it's greatly appreciated, and I look forward to hearing what folks have to say. And that ends my presentation, and I see if there's any questions. I don't know, I'm not exactly sure how the question thing works, but if there are any questions, I'll see if I can answer them.
Unfortunately, Chris, we don't have any time for questions, but we're going to move some of those over to the Slack.
Okay, I will be there.
Yep, have some discussion over there.